Okay. So just saying, recapping what I just said. I said the equivalent of Coulomb's law in magnetostatic is the Biot-Savart Law. So let us start off by looking at the definition. So Biot-Savart says, consider a conductor carrying a direct current I and a steady magnetic field produced around it. So here is your conductor carrying I, and there's a magnetic field around this conductor. The Biot-Savart law allows us to obtain the differential magnetic field intensity, DH. What was the differential electric field intensity?
EL, sir.
No, the differential electric field intensity. What was that? When we studied Coulomb's law.
DE, sir,
DE.
Q
right?
by 4 pi epsilon naught.
Right. So DH is the equivalent now to DE in magnetic field. So the electric field intensity, DH, produced at a point P due to a differential current element, IDL. So here is your differential length. And your current is flowing through that. So your differential current element is IDL, right? So this shows you everything. This is I going through the conductor of length L for your differential length, DL, and your differential current element is IDL. And you want to find your differential magnetic field intensity, DH, at P. So P is at a vector distance R from your differential length of current. Right? So consider differential length DL, hence the differential current element IDL. This is a very small part of the current carrying conductor. The point P is a distance R from the differential current element. The zero is the angle, or the theta is the angle between the differential current element and the line joining point P to the differential current element. So this is your theta. All right. So Biot-Savart law states that the magnetic field intensity, DH, produced at a point P due to a differential current element, IDL, is proportional to the product of the current and the differential length, the sine of the angle between the element and the line joining P to the element. and inversely proportional to the square of the distance r between P and the element. Okay. So it's directly proportional to DL and the sine of this angle, and inversely proportional to your vector R. So when you put that now mathematically, DH is directly proportional to IDL and sine theta. And it's inversely proportional to R squared.
Sir, how does the theta vary? Is it that it varies by the magnitude of the current, or is it the direction of the electrons like flowing? Or
No man, theta is fixed. Theta is the angle between the wire and your vector R.
all right, sir.
Okay. So DH is directly proportional to I, DL, and sine theta. And it's inversely proportional to R squared. Of course, I am, hold a sec for me, please. Yeah, Ned. There. I'm going to show it to you about 12 o'clock because I'm in a class. No, man, I'm online, but I just picked up because I haven't heard from you for so long. And I just see a number of article. Yeah, so to get rid of the direct proportionality and replace this by an equal sign, we introduce a constant K. So K is your constant of proportionality. Now, K, and all these are determined experimentally, is 1/4 pi. So DH equal I DL sine theta upon 4 pi R squared. You remember what DE was?
Differential electric field, sir.
Yeah. I just want to show you the similarity with DH and DE. So tell me what DE was.
So in terms of Q over 4 pi epsilon naught R squared, then that is the unit vector.
Okay.
But
So,
there is no.
so you see, there is quite some similarity between DH and DE. So this equation is general. Now, if we express in vectors, right? Let DL equal magnitude of vector length DL, and AR the unit vector in the different direction of the differential current element to point P. Then DL cross AR equal DL AR sine theta. Remember the definition for cross product?
There's AB, A times B, modulus A modulus B sin theta. Is it cos theta?
So
So
all we do is
AB over sin theta.
replace this by cross product, right? So we get this. And as before, AR equal R over the modulus of R, which is equal to this. So this is the mathematical form of what Void Savart said above. Now, let's go through this verbiage carefully. According to the direction of cross product, the direction of DH, which is this, is normal theta towards the line joining the element to point P. So this is your angle. So you have to turn right going towards R. Is made up of all such differential elements. So, in other words, we look at just a differential element, a little part of the wire. But the wire is made up of infinite amount of these small elements, right? So if we want to find H for the entire wire, what would we have to do? That's a question.
So you could integrate both sides of the equation.
We have to integrate this, right? So H, the magnetic field intensity, is the integral of this, which is the integral here. So it follows closely to what we did in electrostatics. So if you paid attention to electrostatics, you will have no problem here. We can finish this in one lecture. All right.
Yeah, would have anything to do with the wire in terms of the DH.
The DH.
Yes, sir. Because like if it is a shielded wire or if it's just exposed wire or anything like that. So,
see what you're asking. No, it will not have anything to do with it.
okay, all right.
However, the medium, which we'll get to, that is the space between the wire and the point, will come into play. All right. So the closed line, because yeah, you see your integral, is a closed integral. So the closed line integral is required to ensure that all the current elements are considered. This is because current can flow only in a closed path. Right? If you have an open circuit, you're not going to have any current. So it must be a closed path. If the current element is considered at point 1 and point P is at point 2, as shown in that figure, dH2 is I dl1 cross AR unit vector between 1 and 2, 4 pi R1 and 2. Where I1 is the current flowing through DL1. DL1 is the differential vector at point 1. AR1 is the unit vector in the direction. Okay. Now, before I go, you must have a question, man. What's your question? What's on your mind?
Yes, sir, I don't see any wires, so I'm not sure what will be carrying the current. If it's the entire surface, how it will be distributed inside of.
No, I'm not asking for a question with what is on the screen now. I'm asking for a question with what we have discussed so far. With the wire.
Oh, sir, I really have no question. I just try get it for cement. So try get a grasp of it, everything. But can continue, man.
Can continue.
In my eyes.
Everybody feel the same? Okay.
Wait, sir, is the contour integral over the dimensions of the wire? Sir, I wasn't following that. So. Like with the Gaussian surface thing, if it's something.
No, the closed integral, right? Meaning that if you don't have a closed circuit, right, you cannot have a current flowing, right? So all the closed integral means is that you're integrating through the length of the circuit. It's not like in electrostatic where you have a point charge. Because look at it this way. Your differential element, DL, right, would be quite similar to a point charge in electrostatics, right? But here, we are saying that you cannot have a current I flowing if you don't have a complete circuit. So when you integrate, you are integrating over the entire circuit. You with me?
Yes, sir. It's
No,
like on the wire, the light post, it would be the entire length of wire or something like that.
exactly. All right. Because when you plug in your phone, you have one wire carrying the current one way and one returning. That's all. So it's a complete circuit.
Yes, sir.
Digest this again. Because what we're gonna say now. As long as you appreciate that, we're good. So we have ideal one representing your wire, right? Now, again, like in the case of electrostatics, we have a point charge, then we moved on to a line charge, where we consider a line as a string of point charges. And then we move on to a sheet charge. And then we move on to a volume charge. Now, we are saying now, so far we have looked at a line charge. Now let us look at, no, we have looked at a wire, a line carrying current. So now let us look at a sheet of current. So consider a surface carrying a uniform current over a surface as shown in this figure. All right. The surface current density is denoted by the vector K and is measured in amperes per meter. Thus, for a uniform current density, the current I in any width B is given by I equal K times B. You get it? This is K, and this is B. So K is current amps per meter. So for this dimension of surface, your total current I is K times B, where B is the perpendicular to the direction of current flow. Thus, if ds is the dimensional surface area considered of a surface having current density K, then IDL become KDS. Get that?
It's like with, sorry, can go over because I'm thinking about the J with the current density. Something supposed to be normal to the surface.
Right, but it is normal to the direction of flow. So here we have the sheet, right? And current is flowing like this. Right? K is your current density, which is your current per meter. It's normal to the direction of flow. So this is your length. In other words, if one, look at the line, and one is going through per meter, right? So if we have 4 meter, then it's 4, right? That's all it's saying. So I equal the current density, which is 1 per meter, going this way, times the amount of distance, which is 4. So I equal KB. So IDL, now if you look at the entire surface now, right, IDL would be the same as KDS. And if it was a volume, IDL would be JDV. Digest that. Did I digest that it?
Sir, I will only saying if the current is not going in a straight line though, but because of the electric field strength, then it should be in approximately straight line. So I mean there is no collision because I don't see any wires, so I don't see how the charge is flowing throughout the surface. But otherwise it makes sense.
No, but your wire is a sheet, is a plate. So just consider your tabletop. So the current flowing through your tabletop. All right. So the entire tabletop is the wire.
Is by okay, so it's conduction, but just through
A sheet instead of what? Your sheet is a wire.
this.
Right? And in the case of the volume charge, dV, right? You, if you consider your conduction now through to a rod. The copper rod would be your wire instead of, it would be a bigger wire than your normal wire. You get it?
Yes, sir. So you take the size, increase dimension into consideration.
Yes, that's the dV, because J would be in amps per meter square, and you multiply it by the volume to give you the total current. So we are looking at an infinitely long straight conductor. Right? So we are going to align this conductor along the Z direction. So your DL is DZ. So IDL is IDZ in the AZ direction. So your R12, look at this now. We are considering this differential length. Yeah. All right. What the hell is going on with my phone? Hello? 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 So your DL is your DZ. So here is your differential element here. Right? This is your point. This is your origin. This is your coordinate system, X, your Y, and your Z. So R12, your vector R12, right? Look at it. Here, minus ZAZ plus RAR. This is your point. And you want to measure your field intensity at this point. So in terms of vector, you have to come this way. Well, this is the point from 1 to your point P. So you have to come minus Z in the AZ and R in the AR. So your R12 is minus Z AZ plus RAR. All right? You get this? You get R12?
Yes, sir. That part is straightforward.
Yeah. So your unit vector is this as before. And DL cross AR. You should be familiar with that from your matrices. So then, when you do all of that, dH comes this, simplified to this. And then the wire is infinitely long, so you go from minus infinity to infinity. Right? So you integrate this from minus infinity to infinity. And when you do that calculus, let me go back up here so you can have it recorded, so you can follow it. So when you do that math, you come to H equal this. So for infinite long conductor, H is given by I over 2 pi r A phi. Now, in electrostatics, D is epsilon E. The equivalent for magnetostatics, you have B, which is the magnetic field intensity, is mu H. So the magnitude of magnetic field intensity, H, is not a function of phi or Z. It is inversely proportional to R, which is the perpendicular distance of the point from the conductor. It is inversely proportional to the direction of H. Now, the direction of H is tangential, that is circumferential along H phi. The streamlines, that is magnetic flux lines, are in the form of concentric circles around the conductor. Thus, if conductor is viewed from the top with I coming out of the paper towards the observer, then the streamline are anti-clockwise. All that is saying is that the magnetic field lines goes around the conductor. All right. I'm not gonna do this one. We're not gonna have enough time. So when we come back at 2 o'clock, before we do a couple of examples, we are going to do the H for different current flow, like this, the circular loop. We're gonna do those two. And then we're gonna find a couple examples.
Sir, do you know of any ready any experiments you can consider to get a better understanding of Biot-Savart Law?
I can give you the some homework using the MATLAB, where we'll show you how the fields flow, or the streamlines flow when the current flows through different configuration. So remind me before we leave the class later to try and find a couple of examples for you. And I just give you that as homework. All right, so see you at 2.
All right, sir.
It's 2, right? Not 1, 2.
Two, sir.
Yes, sir. 2.